In today's lecture, we're going to continue our deep dive into functions, and today we're going to get slightly more acquainted with lambda functions and lambda calculus. This is going to be a very shallow introduction to the topic of lambda calculus, because that's a rather huge topic in itself. And before talking really about the lambda function, which is so dear and important to us as functional programmers, let's just say a little bit about what lambda calculus really is. So lambda calculus was invented by Alonzo Church in the 1930s. And he was a mathematician and he was working on formal logical systems. So he was just interested in logic. And that's exactly what lambda calculus is. It's a way of expressing logic in terms of pure function application, using nothing but functions. Now, this might sound a little bit abstract, and I can tell you it is pretty. And you'll see some examples of it. It's pretty mind-bending. And the reason why we really want to look at this in this course, in this context, is just to show you the incredible power of functions that pure functions provide. This is an absolutely amazing abstraction. It's not objects, it's not modules, it's not procedures, functions. Yeah. So this is sort of one of the reasons for doing this. The other thing that one can see is that lambda calculus provides us with a universal model of computation. So it's really equivalent to any kind of Turing machine. So that means that anything we can compute with sort of in the Turing world, we can do with lambda calculus, which is kind of nice to know. So we are not limited by going down this path. Lambda calculus comes in two flavors. So Alonzo Church, he first invented his lambda calculus, and he was really happy about it, until his students found out that it was a little bit too general. So you could actually express things that were mathematical paradoxes in lambda calculus, and that of course wasn't good. So if you are a mathematician and you end up in that situation, you basically failed. But Alonzo Church didn't want to give up because he saw that there's something to this system. So then he invented something which is called typed or simply typed lambda calculus, which adds additional terms on top of it so that you can restrict the application of lambda calculus and avoid those paradoxes. Now it turns out that aspect of it is hugely important for type theory and for types in computer science. But that's a different story, and that's something we're going to talk a little tiny bit about in the next lecture. And from now on, we're just going to be concerned really with the untyped lambda calculus. That's the bread and butter for us as programmers. Because we're not mathematicians and we don't really have to care if we can end up in some weird little corner case with a paradox. We call that a bug, and we're done with it. Fine. Yes. So that's the story of lambda calculus. And in a moment we'll go through a few examples and I'll show you some of the incredible power of this. So for example, one of the things that we can do with lambda calculus is we can define things like numbers. So I'm going to show you how to define the natural numbers in terms of lambda calculus. And one of the interesting things is once you have natural numbers, that's the numbers from 0, 1, 2, and so on, up to infinity. Once you have those, you can start defining rational numbers, which is essentially sum n by n, where n is a natural number, as long as that one is not 0. Yes? And once you have those, you can do a series of rational numbers, and then you end up with the real numbers. And once you have real numbers, of course, you can generate complex numbers. So once you are able to define the natural numbers like this, you basically have any number that we can express. Mathematicians, please don't shoot me if I say something stupid. So that's pretty amazing, and this is going to be done purely in terms of function application, and we're not even going to know what the function is. So that's nice. Some of the other things that we're going to be able to do, we're going to be able to do booleans, and pairs, and lists, and addition, and subtraction, and multiplication, and so on. I'm not going to go through all of these. I'm going to show you the simplest ones because one of the features built into Lambda Calculus is that it gets tedious as once you start going into it. So we're just going to look at the really simplest examples. And if you're interested in this topic, please feel free to spend the next week or two just toying with lambda terms. It's great fun. It's like a very high level Sudoku. Trying to piece things together. It's mind-bending beyond recognition. So what are these now? Let's skip Lambda Calculus for a moment and just look at Lambda Functions. So we're going to go through a little bit of nomenclature. This is just if you ever read some of the literature, it's good to be acquainted with this. This is not something that we really need to use in our daily work. So the way we define a lambda function is by saying lambda. And this is the thing, all lambda functions have the same name, unless we name them explicitly. So they're all called lambda. That's why we call them anonymous, because they're just functions. So this lambda here says, now is the start of a function definition, and I add a variable, and I add a dot, and I can add a term. So this is, the whole thing here is called a term, or a lambda abstraction, and this is called also a term. This is a variable, and this variable is bound by this lambda function. This t here, I haven't said anything what this t is, but we can just consider it for now to be something called a free variable. And this one is bound. Right? So this is just jargon, really. And the whole thing here is called a lambda abstraction. So this is a lambda function. Now, if I would do this in F# or Python or whatever, this would be in F#. This is the keyword fun x arrow t. But this is how the mathematicians and lambda theoreticians like to type it. Lambda dot. So this is this part, and that's that part, and you separate them with a dot. And of course, as we've learned, functions take only one argument. Lambda functions do take only one argument. But then we cheat by just typing things in a more terse manner. But the essence of it is, it takes one argument and produces one answer. All right. So what can we do with this thing? Well, we can apply it. So lambda application, so we would take this function lambda x dot t, we can apply it to some value s. What this means is that s replaces x inside of t, this t expression, whatever it might be. So this is something that also is called, one can say that when this happens, you do this is called beta reduction. So what you can do is, after you beta reduce this thing, is you can take this expression here, t, to remove the lambda and the s and everything, and then you say t, where any x occurring in t has been replaced with s. So this is the beta reduction. Yeah. So there's two more things and names we're gonna learn, and then we're gonna just start speaking normal F sharp again. There's something called alpha conversion, which states that, suppose now I would have let's do another example of a lambda, so this becomes clear. So suppose now I would have something like lambda x dot, and this would be something like x squared plus 1 minus y, where this x is bound through the bound variable here, and this is a free variable, this y in this expression. Now, where does y come from? Well, that needs to be defined in some higher scope. So there must be some lambda thing here which defines y, which sort of encompasses this expression. So y is free in this one, but it's not free in the whole thing, because otherwise we wouldn't know what it is and we couldn't really do anything with it. So that would be an error. Now, what alpha conversion says is that I can rename x to whatever. So I can call it q. But if I do, I need to replace it in every place where it occurs throughout. So if this y here is some expression which contains some x's inside of it, I need to go down the line and replace that x all the way through, which is kind of natural if you think about it. This is just alpha conversion is really what we would, as programmers, say, this is refactoring. I type like a monkey. Refactor. That's alpha conversion. We can rename stuff. But if we rename, we need to rename everywhere when it occurs. Otherwise things go horribly wrong. Yes? We know that. There's no magic. And the last bit we actually already touched upon. And that's if I have a situation like, okay, let me get rid of this. This one is important actually, and this is slightly sort of mind-bending for those who aren't super familiar with functional programming. And this is the so-called Eta Conversion. The name isn't important, and this is not going to be in any exam. But what this means is that if I have some lambda f, lambda x, something. Sorry, f applied to x. So what I have here is a lambda which returns a lambda which then returns the first one, f here applied to the x. And what Eta conversion says is that then this is the same thing as f, which means simply that I can get rid of the x's. Yes? This is the same thing as in high school math, when you have x on the same both sides of an equation, you can get rid of it. So if you would just to do a normal, so if you would have some sine x times 5 times x equals x something times some expression. Now you have x occurring on both sides, you can actually get rid of that one. One way of looking at it is that you multiply both of these expressions with 1 over x and 1 over x, and it sort of divides out. It's unity. Same story here. So that's the Eta conversion, and that we use actually quite a lot. In particular, if we do so-called point-free notation, which I will talk a little bit about at some point. Some people call point-free notation pointless notation. I'm a great fan of it, although I shouldn't be, because it can make code really hard to read, but I love it. It's so compact. Okay, so that was a little bit. Now we've sort of passed the formal lambda blah blah. So let's get to the meat of this. Okay, so we already saw this in an example in F#, is that if we have something like lambda x, lambda y equals x plus y, for example, it's tedious to write this. So what we actually do is that we say just lambda x, y equals x plus y. So we skip the one lambda. It's implied. Oh, sorry, dot. Ooh. Yes. Okay, so let's look at the application and beta reduction. Just do an example of it. So we can take this expression here, and now I can apply it to, say, 2. So what does this mean? Well, that means that x becomes 2, and I replace 2x with 2 everywhere it occurs. This is the beta reduction step, so this leaves lambda y. Since I got rid of the first lambda, dot, and then I have x plus y, x, anywhere x occurs is replaced by 2, which we can then apply and do, so we get lambda y is 2 plus y. And now we can do alpha conversion, and then you can say lambda x equals 2 plus x, if we like to. We could just rename y, or we could rename it whatever. Yes? So here we did now the beta reduction, and then we did the alpha conversion, and yeah. But note, we can't get rid of, here we can't get rid of the x. We can't do an eta conversion here. Not in this form. I could, but then I'm not going to get into it. So, by rewriting this slightly. Anyway, so that was an example of applying a lambda function. And now we could, of course, apply this again to, say, 5, and we could do the beta conversion, and then we could la la la, and then we would end up with having the whole thing being equal to 2 plus x with 5, and then that would end up being 7. We're done. Pretty pointless. All right. When I type lambda x like this something, we don't really know what this here variable here is. It could actually be that we feed it in a function. And that becomes sort of evident from then basically the term that we have here, whether this is a function or this is a variable. And this is the same in F# and in Haskell and other languages. So if we could say something like lambda f, lambda x, fx, then it's evident from the term here that that must be a function accepting an x. So that's basically the essence of lambda functions. And then now we just have a few small examples to look at before we conclude. And those are going to be kind of mind-bending. But one thing that you might be wondering is like, okay, so now we've seen this, but in recent times, even languages like C++ and Java and C# and everybody's getting lambda functions. What's the big deal? Like, so what? I can define a function wherever I want. when I encountered lambda functions for the first time in Python, I thought, yeah, what? So what? But really what the essence of a language having lambda functions means is that you can pass in functions as data to your functions, and they can return functions. So suddenly, by having lambda functions, you have first-class functions in your language. Functions aren't these special things. They're just, there's no difference between an integer and a function from a data perspective, or sort of using them. And that's the essence of lambda functions in programming languages. Another thing that I want to point out is that when we're talking about these formal systems and we're talking about the power of these lambda functions, these are pure lambda functions. You cannot do I/O in them. But if you're in Python or in F# for that matter, C#, C++, nothing in the world prevents you from actually doing some I/O inside your lambda functions. Don't. You are breaking logic. It's a bad idea. Keep them pure. Always. All right. So, the first little example of the power of lambda functions that we're going to do is the so-called church encoding. Encoding of natural numbers. And the first thing, and this is kind of interesting because this is mind-bending stuff, really. Because this has, in my opinion, has almost philosophical implications of what actually a number is, what something is, and what a function is. This goes deep, this rabbit hole, and we're going to see more of this when we are talking about stuff like continuation passing and stuff like that. And we're going to return to this subject. But the way this is defined is that you say lambda f, lambda x, e. This is the definition of 0. So for now, we're just going to say this is how we define 0. We take a function, or maybe it's a function, I don't know. We take a some variable, and we get the variable back. So from this, just looking at this, there is no way we can sort of how would this be 0. But let's look at another one. So how did I? Oh, yeah, sorry. Yes. So this is 1. And I guess you can figure out what 3 would be. And this is now becoming interesting. Because now we can see what sort of that there's sort of a what is 0? So if we think of f here as it's a function, it's something that we can apply, obviously. It needs to be a function. This is a verb, right? This tells do stuff with x. Yes? And here we do it 0 times. 1 means do it once. 2 means do it twice. 3 times, do it 3 times. Yes? Count 0, count 1. Yeah? So this really is kind of mind-bending in sort of what a number is really. And note that I haven't said anything about what f is. That's deferred. So this could be 10 This could be eat, pick, launch missiles, whatever. How many? 1, 2, 3, 4. Yes? We don't really know what it is, but we've still been able to get a definition of the natural numbers this way. So that's pretty interesting. Okay? So the second example, which is still a very simple one, because you can imagine this stuff is going to get really, really hairy quickly. So the next stuff that we're going to look at is the definition of true. And false. So how does this work? Well, we can think about this. We learned about partial application where we apply just once. So if we take this definition of true and we now apply it to some value, say 5, then I'm left with a function of y, but there is no y occurring on this side anymore. And that means that whenever I'm going to call that function of y, it's going to give me back 5 and 5 and 5 and 5. And we actually have a name for this function. This is what is called a constant function. It's a function which is just giving you back a constant value. So we do the same thing here. Nothing happens. But I'm left with a function which, whenever I give it, will give me back the same value, whatever I put into it. That function has a name which is called ID. So how does this become true and false? And why can't we swap these and just say, well, it's just a matter of definition? No. See, maybe we could, I don't know, but I don't think so. This here looks very similar to a thing we've seen very recently. So if I replace x with f and y with x, this here was our definition of 0 in the church encoding. So then you can see suddenly that there is a connection between the value 0 and falsehood, which should be familiar to most programmers. If 0, then all right. Which means that now we have suddenly invented flow control in our program, main language here. We can do a function called if then else, where I'm going to say lambda p, lambda a, lambda b is p a b. Right? So what's going on here? So if you've ever programmed Lisp, this would be hugely familiar to you. This thing here would be called cond. All right, so p here. Let's say that p here is now a Boolean. So I give this thing a Boolean, which we know from here is a function of 2 variables. And I give it 2 lambda expressions, 2 lambda terms. I don't know what these are, a and b. I have no idea. These might be, who knows? This might be just values, or it might be, yeah, they might be functions, they might be, yeah, complicated things. So if I now take this definition here, when I say this is the body, and if I would apply true to this function, so p is now true, what happens? Well, the true function says it takes these two values and it returns A. If it's false, it takes these two things here and it returns B. So, if then else. All using functions. You don't even need a programming language for this. Huh? So the final little example before we conclude is going to be the pair, a tuple, which is sort of halfway to a linked list, and you can do the linked list yourself, right? So define a pair. And that we're going to define like this as lambda x, y, f. F, x, y. Right? So how is this a pair? So what are the properties of a pair? What is a pair? Well, a pair is a thing which stores two things in it, and you can pick out the one or the other. That's the only thing you can do with a pair, really. You can put stuff in and you can take stuff out, right? So here's the stuff we put in. So if I would partially apply this pair thing with the values 1 and 2. Now I put 1 and 2 into this thing and it returns me a function f. Now we can define some functions f, s, t, which was the sort of thing to pick out stuff from a pair, as p, t. Now, if you remember how we would use a thing like that, we would say fst on some pair p, right? Which is this thing. So this here expects to get a pair which has been filled, which again is just f, which expects a function which is true, which picks out the first one. So that we can do the other function, which is s and d, which is lambda p, p, f. And now I can pick out the second element, project out the second element from this pair by applying f. So I know this stuff is stretching your sort of abstraction muscles and your Sudoku muscles, but really sit down and try to do these in F#. Code them. You can just write them straight down by saying let fst equals fun p. So, and you can do the pair, you can do the booleans, you can do everything. Just go in, just do the F#, check it out, it works beautifully. It's hilariously fun. And now I have a meeting starting in 5 minutes, so that was all for this lecture, and then in the next lecture we will talk a little bit about types and the usefulness of types and how they enter this crazy world. Until later.